Welcome children. In our previous session we discussed the derivatives which were obtained using the chain rule. Today we are discussing the derivatives of implicit and inverse trigonometric functions. First you need to know what implicit functions are. You can see here I have written two relationships between the variable x and the variable y. Okay, first one is x minus y minus pi is equal to 0. If you see over here, it is possible for us to express y entirely in terms of x. See, we can write y is equal to x minus pi. But when we come to the second one, it becomes difficult for us to write y entirely in terms of x. Okay, so these type of equations or equations only where we are unable to express one variable in terms of other variable entirely, that is implicit function. And this one is explicit function of x because we were able to convert y in terms of x. So in this session we will see how these type of functions are differentiated. This one we have already done earlier also. This can be differentiated by differentiating y with respect to x, and the derivative was entirely in terms of x or a constant. But when we will deal with derivatives of these type, on differentiating y with respect to x, the derivative will be in terms of the variable x as well as y. Now moving on to the derivatives of inverse trigonometric function, some of which I will be proving for you. See, it says if y is sine inverse x, then the derivative of y with respect to x will be 1 over square root of 1 minus x square. Let us find it using the first principle method. This equation can be written as x is equal to sine y. Okay, now if I take a slight change in x, then corresponding to that there will be a slight change in y as well. It can be an increase, it can be a decrease also. Now if these two equations be simultaneously subtracted, then x plus delta x minus x will be equal to sine y plus delta y minus sine y. So the left hand side reduces to only delta x and the right hand side can be simplified. We can use the formula for sine A minus sine B over here to simplify it. So it will be 2 cos sum of both the angles divided by 2, and the next term will be sine difference of both the angles. If we subtract both the angles, you will see y gets eliminated and we get delta y over 2 here. Now dividing both the sides by delta y, the left hand side reduces to delta x over delta y, and the right hand side we can write it as cos 2y plus delta y over 2, and then sine delta y over 2, and you can see we are dividing the expression with delta y. So I am writing that here, and this 2 can be taken as the denominator of delta y. Now if I take reciprocal of both the sides and we assume that the change in x is negligibly small or it is extremely small, almost approaching 0, that will give us the derivative of y with respect to x. So evaluating limit delta x tending to 0, delta y over delta x. Keep in mind I have taken reciprocal of the left hand side, so we need to do that on the right as well. Now because right hand side is entirely in terms of y and we are aware as delta x will approach 0, corresponding to that delta y will also tend to 0. So we get limit delta y tending to 0, 1 over cos 2y plus delta y over 2 into limit delta y over 2 tending to 0, because if delta y is approaching 0, obviously delta y over 2 will also approach 0. So this is what we are getting. Now applying the limit, we get dy over dx as, see, this part will reduce to x. because we know limit x tending to 0 sine x over x is 1. So if we take reciprocal of both the sides, that will also come out to be 1 only. And over here, if we replace delta y by 0, see what are we left with. It is only 1 over cos y. That is what we are left with. Okay, but because y is an explicit function, you can see y is entirely written in terms of x, so derivative of y with respect to x should be in terms of x. So we are going to change it. We can write it as dy over dx is equal to 1 over square root of 1 minus sine square x. Okay, so because, sorry, not x, it will be y. We know that cos y can be written as 1 over cos y can be written as square root of 1 minus sine square y, and we have seen sine y is how much? It is x. So that gives us the derivative of sine inverse x as 1 over square root of 1 minus x square. Over here, children, x belongs to the open interval minus 1 to 1. Okay, x cannot be 1 and minus 1. You can see, though if we talk about domain of sine inverse x, it comes out to be close interval minus 1 to 1, but here x will belong to open interval minus 1 to 1. Look at the derivative. For x plus 1 or minus 1, the denominator becomes 0. So at those points we are not able to differentiate it, so it will be an open interval. Now in the same manner, you can obtain the derivative of cos inverse x. This I have written directly. So if y is cos inverse x, dy over dx will be minus of square root of 1 minus x square. Again, for all x belonging to minus 1 to 1. You can see the derivatives are same. They only differ by a negative sign. Now let us derive for y is equal to tan inverse x. We can write it as tan y is equal to x. Again, if I take a small change in x, corresponding to that there will be a small change in y. Okay, so x plus delta x will be tan y plus delta y. And if we subtract both the equations, we get delta x is equal to tan y plus delta y minus tan y. So you quickly recall, what can you write for tan A minus tan B? Tan A minus tan B can be written as tan A minus B into 1 plus tan A into tan B. So this is the formula I am going to apply in order to simplify it. Okay, so here we find delta x is now tan sum of both the angles. When we add both the angles, we get only delta y. Then this multiplying with 1 plus tan of A into tan of y. Now dividing both the sides by delta y and then taking their reciprocal, let me do it in one step. If I write it as delta y over delta x, this will become delta y over tan delta y into 1 plus tan y plus delta y into tan y. Now apply limit on both the sides. That delta x is very, very, very small. So it is approaching 0. And on the right side, using the limit delta y tending to 0. I will rearrange these terms. We can write delta y with tan delta y, and the other term can be written separately. Limit delta y tending to 0, 1 over 1 plus tan y plus delta y into tan y. Now substitute the value. See, this reduces to dy over dx. Okay, and we know limit x tending to 0, tan x over x is 1. So this will reduce to 1. On the right side, on the other part, we get 1 over. This delta y will tend to 0. So this will become tan y into tan y. We are getting 1 plus tan square y. So this is 1 over sec square y. Is it or not? Okay, let us not convert it to this form because we already know tan y is equal to x. So we don't need to convert it to sec square y. We can convert it from here itself. You can see this equation, tan y is equal to x. So replacing tan y by x, we get dy over dx is equal to 1 over 1 plus x square. Got it, children? Then in the same way, we can derive the derivative of cot inverse x. You will find the derivative is same as tan inverse x. It only differs by a negative sign. So if y is cot inverse x, dy over dx will be minus 1 over 1 plus x square. Okay. And if y is sec inverse x, dy over dx is 1 over x into square root of x square minus 1. In cosec inverse x, the derivative is minus 1 over x into square root of x square minus 1. So you will see sine inverse x and cos inverse x have same derivative. It only differs by a negative sign. Same thing is observed in case of derivative of tan inverse x and cot inverse x. And exactly the same thing is noticed in the derivatives of sec inverse x and cosec inverse x. You will find every function which is starting with c, inverse trigonometric function, like cos inverse x, cot inverse x, cosec inverse x, their derivatives are negative of the other function. Like cos inverse x has derivative negative of the derivative of sine inverse x. Cot inverse x is having derivative which is minus of derivative of tan inverse x. Cosec inverse x is having derivative which is minus of derivative of sec inverse x.